Last video, I talked about the cross product and how that can be expressed using determinant. This was a problem from Hefferon chapter 4. And I tried to emphasize insight. Mathematics is not about calculation. Mathematics is about insight. Why are these things happening? Because if you understand why, then you can apply in different situations. If you just calculate, you can only repeat the calculation. Right? Now, I want to take the same approach or similar approach with this problem. Prove that the area of this region in the plane is equal to the value of this determinant. Okay, so you have two vectors, x1, y1, x2, y2. You have this determinant. It turns out that this determinant is equal to the area of this parallelogram. Now, most people, and I think the answer key as well, put this parallelogram inside a rectangle and did some stuff with areas. And that's just completely unmotivated. I mean, that's really not telling you why this determinant has this special relationship with this area. And furthermore, it's not generalizable to higher dimensions. You want something that explains that kind of gives an intrinsic relationship between the idea of determinant and the idea of the of this area. Okay, so I want to. I would rather do this determinant than the other one. I'm going to look at the determinant x1, y1, x2, y2. Now we know that this is equal. This is equal to the determinant of x1, y1, x2, y2. But I think that it's more intuitive, and there's a better relationship between this and the other. So we know that row operations don't change the determinant. Or most row operations. Maybe I should, so row operations of the form, if I take rj plus k times rm, okay? Right? If I add some multiple of a row to another row, that's not going to change the determinant. All right. Now, what does that correspond to geometrically? Okay. This corresponds to sliding one vector parallel to another vector, the other vector. Okay. And you can see that here. Suppose I took x2, let's see if I can do this, x2, y2, and I take that goes to x2, y2, plus, let's just say it's plus 1/2 times x1, y1. Okay. What's that going to do? Well, I take x2, y2, then I add 1/2 times x1, y1. Let's do a different color so it's more clear. 1/2 times x1, y1 would be here. Okay. And then here I've simply slid along this line here. Okay. That was nice. How did that line get so nice? All right. Now, remember that the area of the original parallelogram, you have the area of the original parallelogram. Suppose I form an area with this new parallelogram, with this new one. Well, since it's slid parallel, the perpendicular distance hasn't changed, right? So the area is the same. So the area of the new parallelogram is the same as the area of the original parallelogram. Okay, so the parallelogram area has not changed. So, sorry, I got interrupted. But let me summarize this finding by saying that I can perform row operations on my matrix without changing the area of the corresponding parallelogram. Okay, so that's my conclusion. Okay. All right, so let's do a row operation that will be useful for me. Typically, you do a row operations to remove the elements to make the elements in the first column equal to 0. I'm going to make this y1. I'm going to make this to be 0. Okay. So I'm going to have if I take the determinant of this original matrix, and that's equal to the determinant of, if I take this here, let's do it this way. I'll take this here. I'm going to take this matrix and I'm going to let R1 change R1. In order to zero this out, I would have to multiply R2 by y1 over y2 and subtract it. So this would be minus R2 times y2 over y1. Okay, in the case where y1 is 0 already, we wouldn't need to do this, but that's fine. Okay, so so if I do that, then I'm going to get that's equal to the determinant of what? Okay, so if I take x1 minus x2 y2 over y1, so that's x1 minus x2 y2 over y1. Here you can see the determinant popping up here, and this is still x2, and then this is 0, and this is y2. Sorry, did I say this right? This should be y1 over y2. y1 over y2. And you can see that. If I multiply y2 by y1 over y2, then that will cancel that out. So let me just make that a little bit neater. I think it's probably better for me to be very clear about that. Okay, this would be y1 over y2. Okay. So this is y1 divided by y2. And then this is y1 divided by y2. Okay. All right, so I have this determinant. Now, if I look at what the two vectors here are, what are they? Well, I still have my x2, y2, which was in this case, it looks kind of like that. So I still have my x2, y2. But what about this one? This one has no y component. It's pointing along the x-axis. Okay, so this is x1 minus x2 y1 over y2. It's just this much. Now, what's the height here? The height here is y2, right? Okay. Now, if I take this parallelogram, so the area of the parallelogram is just equal to base times height. Okay, and the base is x1 minus x2 y1 over y2. And the height is y2, and that just gives me that's equal to the determinant of the original matrix. Okay, so which is equal to the area. It's equal to the area of the parallelogram. Well, all right. So I'm sorry. Which is I skipped a step here. Sorry. That's equal to the determinant of this matrix, right? So if I take this determinant, you can just see that it's x1 y2 minus x2 y1. Okay. Which is equal to the determinant of the final matrix, which is equal to the determinant of the original matrix. Okay, so that's showing you why. It's showing you the reason why is that row operations which don't change the determinant also don't change the area. Okay, and that's a proof that can be applied in higher dimensions as well. If you tried to divide up a rectangle into areas, if you tried to do that in 3 dimensions, you would pull your hair out. But this proof you could use